Hi everyone! Today let's talk about section 14.3, conservative vector fields. So we want to try to answer the following two questions. When can a vector field be expressed as the gradient of a potential function? A vector field with this property is called conservative vector field. What special properties do conservative vector fields have? So before we get into that, let's introduce some basic definition about types of curves and regions. Simple and closed curves. Suppose a curve C is described parametrically by R of t, where A is less than or equal to t, less than or equal to b. C is a simple curve if R of t1 is not equal to R of t2 for all the t1, t2 which are distinct. Okay. So because they're distinct, so here it should be less than. Okay. i.e., C never intersects itself between its endpoints. Okay. So next, C is closed if R of A equals R of B, i.e., the initial and terminal points of C are the same. Alright, let's see here. Let me draw some picture. First picture, this is the first picture. Okay, is this a simple curve? Yes, it does not intersect itself. Okay, so this is simple curve. And is it closed? Yes. Because R of A equals R of B, right? This is closed. The terminal points and the initial points are the same. And when we say simple curve, we say it never intersects itself between the endpoints, but not included the endpoints. Okay? Next. Well, this guy, is it simple? Yes, it's simple. But is it closed? No. So this is not closed. Okay, how about this guy? Is this simple? Not simple. Is this closed? Yes. It is closed. Okay, how about this guy? Is this simple? Not simple. Is this closed? Not closed. So far, so good, everybody? Okay. Now, here are the definition about simple and closed curves. Next, let's talk about some region. So we call that an open set only contains interior points. So it does not contain its boundary points. Suppose R is an open region in R2 or R3. Okay, so let's look at the following definition. An open region R is connected if it is possible to connect any two points by a continuous curve lying in R. An open region R is simply connected if every closed simple curve in T can be deformed and contracted to a point in R. Contracted. Okay, so here are some notes. Connected means R is all in one piece. So simply connected means R has no holes. So one piece. Because it's open, let's use dash line. Okay, so this is connected. And simply connected means there's no holes. Okay, so if this guy has holes, it is connected but not simply connected, right? Okay, so R2 and R3, they're both connected and simply connected. So now let me draw some pictures. So if I draw a dashed line here, so this guy is both connected and simply connected. Okay, so there are different definitions, don't get confused. Okay, so connected means it's like just one piece. It does not have like several pieces. Okay, And simply connected means there's no holes. Okay, then let's look at the next picture. So if we have one piece here, the other piece there, what do you say this guy? This is not connected. Okay, but is there holes there? No, so this is simply connected. So any point, any closed curve can be contracted to a single point, right? Can you imagine? Yes. So contrast means so if we have region, we contract it, deform and contract it into a single point. Okay. Next. So this guy has a hole, but it's still an open region. So this guy is connected, but not simply connected. Okay. And furthermore, if we're something like this and this, then they're not connected and not simply connected. So far, so good, everybody? Okay, next. Test for conservative vector fields. A vector field F is said to be conservative on a region if there exists a scalar function phi such that F equals the gradient of phi on that region. Phi is the potential function for F. So here's the test for conservative vector fields. In R2, let F be the vector field, the components functions, the coordinate functions are F and G. Okay, let's say this is vector field defined on a connected and simply connected region R. So we already know what is connected and simply connected means, right? And where F and G have continuous first partial derivatives on R. If F is conservative vector field on R, even only if F partial Y equals partial G partial X. Do you remember why is that? Okay, think about it. If F is the gradient field of phi, well, this is like phi X, phi Y, right? And remember, F is F and G. So remember, in order to be a partial derivative, the mixed partial derivative should equal, right? So that means phi xy equals phi yx. Well, phi xy is the same as fy. It should be equals gx. So this is what we get. All right. So in R3, similarly, now our vector field is going to have three coordinate functions. Then we have the conditions fy equals gx, fz equals hy, gz equals xy. Okay. So far, so good, everybody. So why is that? Because now you have phi x, phi y, phi z. Now, what are the mixed partials? So f, g, h, right? We have f. So the mixed partial, we have psi xy equals phi yx. This is the same as saying fy equals gx. And we have phi xz equals phi zx. This means fz equals hx. And we also have phi yz equals phi zy. So this is the same as saying gz equals hy. So far, so good. Okay, so in R2, we have one condition. And in R3, we have three conditions. So far, so good, everybody? Okay, let's look at the following example. Determine whether the following vector fields are conservative. Then find the potential functions. Okay, so now let's see. Here, this is f, this is g. Okay, so what's fy? Well, fy, we take the derivative with respect to y. The derivative of cosine is minus sine. So far, so good. How about gx? Well, gx, derivative of e to the x is e to the x. Oh, they are the same. Okay, and what is the domain? What is the domain for the vector field? Wow, that's the whole R2. And R2 is connected and simply connected. That's why here, because we have f partial y equals partial g partial x. Now we know a conservative vector field, f is a conservative vector field. So we should be able to find a potential function. Okay, so how to find a potential function? Well, remember f is like phi x, g is like phi y, right? So what is phi? Well, we can integrate the 5x with respect to x, right? 5x is the f. So e to the x cosine y dx. Well, integral of e to the x is e to the x. So we have e to the x cosine y plus d or c. Okay, constant. But c, okay, constant. X is the variable. Constant y is considered as a constant in this case. Okay, so c is actually a function of y. On the other hand, phi is the integral of phi y with respect to y, and that's minus e to the x sine y dy. Integral of sine y is minus cosine. So we have e to the y cosine y plus d of x. So here y is the variable. So x is the constant. So that's why constant means it's a function of x. Now we compare. Okay? Compare. So we compare, well, this term is the same, right? And then here, well, you see, we compare the, so it's, because this is like a function of y, and this is function of x, and because they should match, so which means we can only have a constant. Okay, because if you have a function of x, let's say x, well then look at this, it says that, okay, I should have a constant or function of y. We shouldn't have another x there. Okay, so that's why we cannot have like a function of x. So when we compare, we get the phi equals e to the x cosine y plus a constant c. So far, so good, everybody. Okay, so don't worry, we'll do more example, and then you understand what I mean by compare. Okay, let's look at the following example. So here we have R3, so FGH, Fy equals 2x, right? And next gx, we have derivative of x squared with respect to x is 2x. So they match. And how about fz? So we just check on the list, okay? So fz is minus 2z. hx is minus 2z as well. So they match. And finally, gz is 2, and hy is 2. So they also match. And what is the domain? Domain of this vector field, because they're all polynomials, so domain is everywhere, so R3. Okay, now what is the phi? Well, phi is integral of, so you know, this is like 5x, 5y, and 5z, right? So we can do 5x, so 2xy minus z squared dx. So we integrate with respect to x. Well, integral of 2x is like x squared, so we have x squared y, and z squared x, plus a constant. Constant means does not contain the x, but it could contain y or z. Okay, and then we continue, integrate. The second coordinate is like 5y, so we integrate with respect to y. We have x squared y, and then 2zy. Plus constants. Constant means it has no y in it, but it might have x and z in it. Okay, integral the 5z, so we have 2y minus 2xz dz. Integral of 2y is 2yz. Integral of 2z is z squared, right? So minus xz squared. And plus CDE. E has no z, so it might have xy. Now let's compare. Okay, let's compare. Now, let's look at this one and compare it with the next one. This guy, we already have it, and this guy, we don't have it. But you see, c is a function of y and z, so c should contain this guy. And this d should be this term, okay, minus z x squared. And so we can think about, like, to replace c of y comma z by the 2zy. Okay, so we write it down. Phi is x squared y minus z squared x, plus compare. This guy should be 2zy, and usually there should be a constant. Okay, now let's check with the so we get this from the upper two. Let's look at the last one. 2yz, oh, we have that, minus x z squared. Oh, this is this term. And plus a function of xy. Actually, a function of xy is this x squared y. See? Now it match. So we're good. So this is our potential function. Okay? So this is what we mean by compare. You integrate with respect to x, y, z, and then you compare. You pick one of them and you see, okay, compare. With this guy, we have it. This guy, we don't have it. So maybe function of y and z is this term. And usually plus a constant. And then also, next one, we have this guy, and this one we already have. So, a function of xy, it should be x squared y. So this is how we compare. So far, so good, everybody? Alright, let's continue. Okay, let's investigate the properties of conservative fields. So here we have the fundamental theorem for line integrals and path independence. Let F be a continuous vector field on an open connected region R. There exists a potential function phi with F equals the gradient of phi. So this means F, the vector field, is conservative. If and only if the line integral along the path C, okay, so of F dot T ds, so this is a line integral along the path C, equals phi of B minus phi of A for all points A, B in the region R and all smooth oriented curves C from A to B. Okay? So if and only, it means we can have this direction, we also have the other direction. Okay? So F is conservative. It is a gradient field of some potential function if and only if the line integrals, okay, along all smooth oriented curve in the region R can be evaluated from we use phi of b minus phi of a. Okay, so we evaluate the function phi, plug in the terminal points b minus when we plug in the initial points a. Okay, so let's continue to look at the next example. So evaluate the following path integral. Okay, so this is the vector field f. And last time we already figured out f is conservative, right? So we already know f is conservative, and what is phi? Okay, phi is, let's see here. This is phi. Okay, let me copy it down. Okay, let me move it here. So phi is x squared y minus z squared x plus 2zy plus c, right? We already show it. This is the potential function. Okay, so this line integrals f, oops. So f dot dr is gonna be phi of the terminal points minus phi of the initial points. Well, that is b, so if we plug in x is 1, so 1 squared times 2 minus 3 squared times 1 plus 2 times 3 times y is 2, right? And we don't need to plus the constant because the constant minus the constant again, it just cancel out. So this is phi of b minus phi of a. Well, x squared, so minus 3 squared, y is minus 2, and then minus z squared minus 1 squared, x is minus 3, and then plus 2z, z is minus 1, y is minus 2, right? Okay, what do we get? 2 minus 3 plus 4 times 3, 12. And then negative 3 squared is 9. 9 times negative 2, negative 18. Minus become plus 18. And then minus 1 squared is 1. Minus become plus 3, but another negative, so minus 3. And then negative cancel, so 2 times 2, 4. But there's negative in front of it, so minus 4. So what do we have? Let's see here. We have this guy. So we subtract 10, right? It's like subtract 10. And we add, well, that is 30. 32 minus 10 is, oh, I realized I have a mistake. Here, it is 9. Okay, so let's calculate again. Okay, so 2 minus 9 is minus 7, plus 12 is 5. 5 plus 18, 23, minus 3, 20, minus 4, 16. So far, so good, everybody? Okay, so that is our answer. See, it saved us a lot of work. And here, you see when we compute this line integrals, okay, so when we compute the line integral, we don't need a parameterization. Right? Because we just find the potential function and then we plug in the terminal points, subtract, we plug in the initial points. Okay? Alright, so we actually don't care what the actual curve C is. As long as it's a simple curve, then we can always find this line integral, okay? Using this method. Okay, let's continue to the next example. So consider the vector field f equals 2 plus y x with the paths. So C1 is the straight line segment from -1, 1 to 1, 1. So and okay, let's see here. So this guy is 0, and this guy is -1, 1, right? We have, this is the x-axis, this is the y-axis, this is 1, 1. Okay, so C1 is the straight line segment from -1 to -1, 1 to 1, 1. And then C2 is the portion of the curve, the parabola. Okay, the parabola. Let me use a different color. Okay, so this is a parabola. Okay, from -1, 1 to 1, 1. So this is C2. C3 is a unit circle oriented counterclockwise. So that's the C3. Okay, find the work integral of the field along these paths using the potential function. Okay, now let's see. Let me change back to my color. Okay, so F equals F and G, right? So we have 2 plus y and x. First, we need to find a potential function, right? So, what do you want to check? We want to check whether Fy equals Gx. What is Fy? Well, that's 1. Gx is also 1. And what is the domain? Oh, because they are all linear functions, domains are real numbers, so all points in R2. Okay, x and y can be all real numbers. Okay, and then so by the test for conservative vector fields, we know this vector field is conservative, which means we can find a potential function. How do we find a potential function? Phi equals the integral of the first coordinate 2 plus y integrate with respect to x. So we have 2x and xy plus a constant of y. On the other side, for the second coordinate, we integrate with respect to y. We have xy plus d of x. Now we compare. See? xy, check. dx, well, this is dx, but there's no other function of y there. So compare. We can get phi is 2x plus xy plus a constant. Okay, so we don't have a function of y there because here there's no y. Okay, next. So after we figure out the potential function, then we can compute the line integrals. So the line integral on C1 f dot dr, this line integral is the same as the work done, right? For force field, for fluid, we have circulation. Okay, so the work is then phi of the terminal point 1, 1 minus phi of the initial point minus 1, 1. Well, let's plug in 1, 1, 2 plus 1 minus plug in -1, 1. X is -1, so -2 and -1. Oh, we get 6. Okay, so and then next, what is the work? What's the line integral along C? You see, it's the same point. So initial function, because C1 and C2, they have the same initial points and terminal points. The work done, the line integrals are actually the same. So that's why that theorem, the fundamental theorem for line integrals and path independence, the line integrals are actually independent of paths. Okay, so you can see same, because they have the same initial points and same end points. Okay, so that's why path is independent. Okay, So we don't care like what the path look like. It could be a straight line, it could be a parabola, or it could be something crazy. Sorry, it has to be smooth oriented. Yes, it could be something crazy. Then as long as the terminal point and the initial point are the same, then we have the same value for that. Okay, now how about on C? Well, on C, what happened? You can think of the initial point is 1, 0. The terminal point is 1, 0 because they're the same point. So it's 0. Okay, so that's why on closed curve, the line integral is 0. So far, so good, everybody? Okay. Let me continue in video part C. Alright, see you soon.